I want to start by reassuring you about this section of the assessment. Rheology often sounds intimidating, but what we're really doing here is putting numbers onto things which you already understand from making your creams and ointments. Rheology is simply the study of how materials flow and deform. You already know what a cream feels like when you scoop it out and spread it or rub it into the skin. Rheology just gives us a structured way of describing those experiences scientifically. In this part of your report, you are not being assessed on advanced mathematics. You are simply being assessed on whether you understand what the measurements mean and how they relate to the behaviour of your own formulations. For your report, one of the key things you must include is a plot of shear stress against shear rate. I want to be clear about what this means in practice, because this is not meant to be difficult. You are not expected to generate the plot from scratch. I've already uploaded the spreadsheet to the key learning environment that contains the data and the graphs already plotted for you. Your task is to locate the correct graph, insert it into the report, and present it properly with a clear figure, number, and a caption with labelled axes. Once the graph's in your report, what I want you to do with it is to make sure that the plot allows you to identify how the cream or ointment behaves when it is sheared. In other words, how stress changes as the shear rate increases. You'll notice that a best fit line has been applied to the data. That is not just decoration, it's there to represent a mathematical model of the material's flow behaviour. Your job is to use that line to describe the type of flow your product is showing and what it tells you about the structure of your formulation. You do not need to explain the mathematics in detail. What I'm looking for is interpretation. Does the stress increase linearly or non-linearly? Does the curve suggest shear-thinning behaviour, which is typical of creams and ointments? If you can insert the graph correctly and explain this in plain words, what the shape of the graph tells you about the product, you're doing exactly what this part of the assessment is designed to test. What we're going to do is just find the KLE files so we can actually get them downloaded and actually look at the graphs. So you'll find those on the module that we have, so that's PHA-20032, and if we scroll down to week 12, and we have week 12 here, and then we go to, we've got rheological data, and we go on to rheological data, and then we've got all the different groups and the different formulations that were produced and tested. And let's just simply double click on here, and that should download the file. And now this will come up in a form which isn't very friendly, and don't use this particular form. Download the file. So we just click on this little download button, and then we should be able to get that to come up in Excel. Okay, now that's downloaded in Excel, and we can actually start working with that in Excel. And it's much easier to explain what's happening in Excel rather than trying to do anything else. Now, what you'll find is you should see a set of graphs come up first of all, and these are the end product of what we're really wanting to see in your report. And we want that these have been done for you, so you basically have to copy and paste them into your report and actually talk about these. And the idea is to actually be able to put proper notation on them, such as figure, and explain what's actually in the graphic, in the caption for each figure. And then what I want you to do is, you don't necessarily have to do this, but if you look back on the data, that's actually been recorded. You've got some nice useful information such as when this was run, what the instrument geometry was. So in this particular case it was a plate and cone instrument that was used to record this, and you've also got this piece of data here that says do not use. Now what was happening there was when I put that onto the instrument, I first of all got that to rotate very quickly the sample and produce a lot of high shear on that, so it's kind of as though I'd put the cream between my hands and gone like that. And the reason for that is that creates a very nice uniform response from the instrument that's very reproducible, and it makes the data much more easy to interpret and straightforward for you at this point. Now, as you move on with this journey in rheology, that won't be the case, and we won't do that pre-treatment, because actually that pre-treatment, that measuring that as it goes onto the instrument is really important, and there's lots of valuable information there. Now, one of the things that it's done is actually broken down any internal structure that's already in the cream, and so you have not got any form of yield stress in there. So that means that one of the models that's used for actually describing how rheology works is no longer necessary to consider. So that's a big hint there on how you can be looking at your data. So there's none of these will be plastic in essence, and this little bit here has actually destroyed the plastic properties by rotating very quickly and shearing the creams and ointments before we've done measurements on them. That's not usual, but it does make your data a lot easier to interpret and a lot more straightforward, because you're only just beginning on this journey with interpreting this kind of data, and it really is quite hard to do. So respect to you for trying to do this, and for everyone that actually takes us a few steps down this journey. So what we'd like is these put into your report and with appropriate comments. So we've got those for each of your creams and ointments, and like I said, they're all on the KLE. So to actually copy them, you're probably going to have to hit this enable editing button that you might see at the top of the screen, and then you can actually copy and paste. Okay, yeah, and that's one of the key bits of writing your report. One of the most important plots in your report is the shear stress on the y-axis against shear rate on the x-axis. The reason we do this is simple. The single plot tells us what type of behaviour the material has. You are not expected to generate these plots from scratch. You already have them prepared for you. Your task is to recognise the pattern and explain what it tells you about the cream or ointment. Now, if we've got a flow index or n value which is greater than 1, we have a scenario which is applicable for the, let's just put a pointer on. We've got this scenario here where we have shear thickening, okay, and this is where n is greater than 1, okay. Now, when n is greater than 1, for example, n equals 2, the line becomes curved upwards. In this case, the shear stress increases faster than the shear rate. As you shear the material more quickly, it becomes increasingly resistant to flow. The obvious example for this is corn flour and water. So when you actually try and put a spoon into there, the more you force that, the more resistance it gives. On the graph, the curve starts gently but then rises steeply as the shear rate increases. This behaviour is called shear thickening. It's not typical in cosmetic creams, but it's useful to understand because it represents how a material that stiffens when it's worked. Now, if n equals 1, we have a wonderful straight line plot. Okay, on the graph it looks like a straight line passing through the origin. Every time you double the shear rate, the shear stress doubles as well. It's known as Newtonian flow. Water, simple oils behave like this. Most creams and ointments don't behave like this, but this case is a useful reference point. It's always useful to sort of think about, does my material behave like water or an oil? Now what we have over here on the far left, right hand side, is we have if n is less than 1, okay, and this is really where we'd expect most of your creams and ointments to sit. Okay, if n is less than 1, for example n equals 0.5, the line curves in the opposite direction. So what we're seeing is shear stress will still increase as shear rate increases, but as it does so, the shear stress increases more slowly as the shear rate increases. So each increase in shear rate produces a smaller increase in stress than before. On the graph, we see the graph rise quickly at first and then gradually flatten out. The shear thinning behaviour is exactly what we expect from creams and ointments, and it means we've produced a product that resists movement at low shear but then becomes easier to spread the faster you rub it. Again, with this particular slide, what I've got going on here is some descriptions, and it's broken down in exactly the same way as the previous slide was, between this non-plastic on the top and plastic flow on the bottom, and trying to give some nice examples that you should have come across and to describe how those materials behave. Some of that I've done in the previous slide while I've been going along, but this is quite a nice slide to just get yourself up to speed with and allow you to sort of try and relate some of those properties of the flow graphs to common materials that you will have handled and used. One of the most easy to get a hold of is like ketchup and mayonnaise. You've also got things like water, milk, toothpaste, and then you've got some of the more interesting materials that cross over here. Okay, and one of the things I really wanted to try and emphasize with this is trying to relate rheology data to a nice simple mathematical model, and the most simple of all is really the power law model, and that gives a lot of flexibility and describes an awful lot very straightforwardly. Now you've got a couple of different components to this, but we'll talk about that a bit in another slide. But this is often described as the power law equation, power law model, power law scaling relationship. You see this arise in other areas as well as rheology, but this is kind of a nice example of that. With the power law, there are some nice simple terms to this, and it's nicely explained in this slide here, where we have our shear stress, which is the torr value, the blue value, and then we have our consistency index, the green K value, which could be described as a viscosity level once flow started. Now the shear rate, that's described very nicely with this. Well, I've made this as a red value. You'll find this actually black throughout most of the slides rather than red to try and prevent confusion. And the flow index, I've tried to keep that purple throughout the slides going forward. And that actually raises this to a power, and it's that power level, or that indices value, if we're looking at it mathematically, that gives that shape to the curve where it's gone from a straight line to a curve. Because when this flow index or n value equals 1, we get a nice straight line, and the consistency index is literally the viscosity. So that's the way of understanding this. It's a nice straightforward model, is this power law model. What I'm trying to do here is explain what the individual terms are in the power law equation. And the two really key terms that I'm really wanting you to focus on are going to be the shear stress. Now the shear stress is measured in pascals, and that's a pressure measurement as well. And the reason for that is because pressure is measured as force per unit area, and shear stress is force per unit area. The difference is that pressure would be a force down and normal to the plane, whereas shear is actually horizontal and parallel to the plane. Okay, so that's shear stress, okay, and it's that movement across, just like a pair of gardening shears. You're going snip, 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 and those are shearing the plants across the stem. Shear rate, okay, that's how fast the cream is being deformed. Now, that's something I really want you to focus on in your definitions at the beginning of your in your report, and try to tell me what that is. That will help you tremendously in your revision. Really don't want you getting that shear stress confused. That's really quite important. Okay, now how we can actually view this is if we try and think of it as a normal piece of maths where we have this y equals mx plus c. Okay, we've simply got our y, which is our torr value, then we've got our k, which would be equivalent of our m, and then this gamma dot or shear rate is what we call our x value normally, and we can think of this as our independent variable that we can change, and we will actually set the machine to actually produce different shear rates, and we will then measure the shear stress. So we've got this is how we're actually taking our measurements and how we're actually getting some values out of the instrument. This particular slide, I'm trying to go through some of the other terms which are in this power law equation, and we've got our green K or prefactor coefficient. Now, when we happen to have an n value here, or indices value, which is equal to 1, that will be the viscosity, and it is a nice pre-value that will simply multiply up the value of the shear rate, and just like you have in your normal line where you have y equals mx plus c, this k value can be thought of as the m value that determines the actual slope of the line. And now that's very nice for when n equals 1. When n is equal to a different value, that's another story. The exponent value here is really the part that actually is the reason why the power law is called the power law, because it raises this shear rate to a particular power and or exponent value, and it's often referred to as an index. There's lots of wording that can be used around this, so trying to avoid that being confusing for you, but it's determined through these log-log plots that you'll have heard of, and that's why you'll see in the spreadsheets that I've shown you there are log-log plots, because it allows you to get to that value of n, or the exponent value. What it does is really determine the curvature or the scaling behaviour of the line. So you can see the line will actually maybe go up and bend over and form a plateau, or it might form almost like the edge of a U shape where it gradually increases as a parabola. This is really controlled by that n exponent value, and this is why we relate this into this power law, because it actually gives you a sense of what that curve is going to look like for a given value of n. Now when n is negative, it will actually decrease the graph. So again, these log-log plots are extremely useful when they give you these values of n. It's quite useful just to look at the different values that you could get for the exponent here, or the flow index, and what you'll actually see is this has really quite a profound influence on the shape of the curve. And what we're seeing is when n is greater than 1, we'll get this curve where it's almost like the bottom of a U shape. It's starting to go upwards and it's inflecting up, and it will go on forever basically. Now when n is equal to 1, we have that Newtonian scenario where this is actually a nice straightforward straight line, very simple to understand. Now once we get to n is below 1, we get this curve that actually goes up to start off with and then curves around at the top, and so it doesn't actually stop increasing. It will continue to increase, but the rate of increase declines as the shear rate increases. So what you're seeing here is this line it won't eventually plateau, but it does appear in this graph as though it is going to go towards a plateau. And then we have the n equals 0, and of course that simply gives n, when n is 0, that means that the number that you're raising it to the power by is going to equal 1. So in essence, what you'll always get for whatever value of shear rate, it will always give 1, and so you have your multiply by your k value, and so you'll always end up with a constant coming out of the equation. And so this gives us a lot of flexibility in our modelling of our data with just a very simple set of numbers. One of the things which I've tried to show in all of the data is the log-log plots for shear stress and for viscosity. And the reason for that is that the slope value on that straight line that you should get produced is equal to this flow index, or this n value or indices value. So when you have a slope where the n is equal to 1, that should be a nice straight line going up at 45 degrees as you plot your log of shear stress against log shear rate. If the value of n is less than 1, the actual slope value should be less than 1, and again if the n value is greater than 1, that slope should be much more inclined. Now, where the actual intercept occurs is equal to this k value, and so but it is important to remember this is the log of k where the intercept is occurring. It's not the k value. To actually get the k value, you have to put that into a calculator, the intercept into a calculator, and then get the antilog of that. Or you can, rather than the antilog, you can say 10 to the power of and whatever the intercept value is, and that will give you your k value out. Again, with this power law model, it's nice and simple, and we'll talk about this a little bit further. Our k value we talk about as being a measure of the fluid's viscosity, because when the n value or the flow index is equal to 1, it is literally, that is the viscosity. So that's true when we're talking about a Newtonian fluid. Now, the flow value or the flow behaviour index n, this is what gives us that shape of the curve, and it's a nice, very simple model that gives you a lot of data, and you can do a lot of analysis from this. The Herschel-Buckley model is probably a more useful model. I've tried to remove this from this particular practical by making sure that the creams were pre-treated so that you didn't have any plastic element to them. However, what it does is give you this sense of how much force you actually have to apply to start some movement occurring, and this is done by what we call this yield stress figure. So it's the minimum amount of stress to initiate flow. It's very useful, especially with creams where you have something that sits really quite still, and if you spoon it out and it actually forms a nice dollop and it doesn't actually flow out any further, that's really a sign that you have a yield stress present and that you need to take account of that. Now, like I said, I've actually removed this from this particular practical so that you don't have to think about this, and so this will make the analysis of the information simpler and easier for you. However, be aware of this particular model. It is by far and away the most useful model. Now, this slide is a little bit messy. However, what I've tried to do is put across all of the different scenarios for these particular scenarios of shear thickening, Newtonian and shear thinning models. And again, I've looked at this from the non-plastic and the plastic flow. For your sake, with the practical that you've done and the data that you're looking at, you're only looking at the top 3 graphs. Now, what you could look at those as is where you have a yield stress of 0 and you're still using the Herschel-Buckley model, where you're saying that the yield stress is just equal to 0. Now, again, with this, what you can see is you've got this shear thickening scenario where the flow index is greater than 1. You've got the Newtonian scenario where the flow index is equal to 1, and then the shear thinning where the flow index is less than 1. So it's really good for you to sort of start relating these nice straightforward models to those flow index values and also to that K value, which in the case of the Newtonian model is literally the viscosity. Something that you should be aware of, don't get too worried by this, and that's that there is a relationship between shear stress and viscosity, and you could think of viscosity as being the differential of shear stress. Like I said, don't get too worried about that. Normally when we talk about anything that is going to be a differential value, we will state that. We normally quote only apparent values, and those are values that are measured by the instrument. You may come across this at some point in the future. Don't get panicked. It is very slightly different, and the reason it's very slightly different is that you have to do this division of the shear rate by the flow index. But don't get too worried by that. That's probably something you'll never come across, but I'm trying to make sure that you can cope with that if you do. Now, what I want to do here is to try and talk through viscosity itself. Now, viscosity is probably a term that you've heard a lot about, and again, it's very simply known as, but the apparent viscosity is simply the shear stress divided by the shear rate. And that's normally what the instrument measures. It's known as the apparent viscosity. It's what this assessment will use. It's what we get out from our instruments. So again, please don't get worried about this. This differential viscosity is calculated rather than measured. It's not going to be part of this assessment. It's not part of the practical. It's unlikely you're going to come across it further at the moment, but be aware it can catch you out if you start looking at a textbook, and that's why I try and make you aware of this, so that that language does not confuse you. Okay, now let's just try and look at this viscosity, this idea of viscosity, when we relate that to this power law model, because the power law model has proved to be very powerful and it's very useful, and we can extend our idea of this simply into this idea of viscosity. So what we can simply do is say that because viscosity is simply a measure of the shear stress divided by the shear rate, we can look to this bottom equation and we can input our values, our consistency index, our shear rate and our flow index into the equation, and then divide that all by the shear rate. And all that simply does, when we look at this, is reduce the flow index by 1. Now that does that very nicely and very simply, and that's for the apparent viscosity only that this does this. So that's basically everything you're going to be looking at in terms of the data here. It's not quite true for the differential viscosity, but again, that's not for this assessment. Now, one of the reasons I tried to make sure that we didn't include this idea of plasticity into the models that you're working with was to, one, make sure that you got some very nice smooth data out of the instruments, but also to try and reduce the number of values you're looking at in this assessment. And so We don't have the yield stress as part of this assessment. However, the yield stress does appear in this viscosity equation that you can see down on the bottom of this slide. And so what that will mean is that you will have that component feeding in even when you've got very low values of shear rate occurring. It does complicate the equation. It makes it much more difficult to fit data to this model. The Herschel-Buckley model is more difficult to fit, and that is partly why I've tried to steer away from that in this particular assessment. Now, I think this is really useful. These are a really useful set of graphs for you to compare your data with, and you should be basically looking towards the non-plastic flow, because I've tried to eliminate the plastic flow from this practical to make sure that it's more straightforward for you. And what we're really wanting to do is to make sure that you're able to say what sort of viscosity profile you're getting from your creams and ointments. And is that shear thickening? Is it Newtonian? Is it shear thinning? And you should be able to look at your graphs and make a comparison to these graphs here and tell me something about that in your report. Now again, there is this log-log transform, and for viscosity that's a little bit different to the shear rate, to the shear stress. And it's very useful just to look towards this. Now, the reason I put this in is because when you actually get shear thinning, your log-log plot will have a negative slope. It will slope downwards, that you can see on this right-hand side graph. So you're seeing that slope go down, and again, the intercept for the consistency index, you get the log value there. But like I said, for the viscosity, the slope is actually sloping down. Now, when you get n is equal to 0, you simply get a flat horizontal line for this nice simple power law model. So that becomes very straightforward to deal with. If you have if your index n is greater than 1, you will see this slope being slightly positive or positive. So again, this is useful to look at and to being able to tell me something about that index value, that flow index value from your data, from the and comparing it to these graphs, and you should be able to put that into your report. When we are talking about sensory evaluation, we are really talking about structured consumer feedback. A group of people are given a product, clear instructions on how to use it, and a set of questions. They are then asked to describe what they experienced when they handled that particular product. This type of testing is extremely important in product development and marketing, because it tells manufacturers what consumers like and what they dislike, and what they can expect the product to feel like. However, consumers do not think or talk in rheological terms. They do not perceive viscosity, yield stress, flow index directly. Instead, they describe such sensations as how much effort it takes to scoop the cream, how much resistance they feel when spreading it, how quickly it flows, how the feel changes when they rub it in, and whether the product feels stable when left to rest. This is where rheology becomes powerful. Rheology sits behind the scenes and allows us to link those sensory descriptions to measurable material properties. If we can reliably connect what consumers say to parameters from rheology models such as the Power Law or Herschel-Buckley model, we can then begin to predict the consumer perceptions from a laboratory test What this means is we can design formulations more efficiently. Instead of repeatedly testing products on consumers, we can use rheological measurements to target what consumers expect, set meaningful specification limits, and support claims about how the product feels. In short, sensory language gives us words, and rheology gives us the numbers that allow us to predict and control our products. Let's start with the very first interaction a consumer has with a cream, which is picking it up from the jar or container. At this stage, the product's under very low stress. There's very little movement, there's very little deformation. Consumers are not spreading this cream yet. Instead, they're just judging how firm it feels, whether it holds its shape, how easy it is to scoop out. These first impressions are extremely important because they strongly influence whether the product is perceived as high quality or poorly formulated. In sensory panels, this is where you hear words like firm, soft, stable, loose, luxurious. What the consumer is really responding to here is whether the product resists movement at rest. From a rheological perspective, this behaviour is dominated by yield stress. Yield stress tells us how much stress is required before the material starts to flow at all. A cream with a high yield stress will feel firm in the jar, it'll hold its shape. A cream with a low yield stress will feel softer and more mobile. This is why the Herschel-Buckley model is particularly useful for creams and ointments. It includes a yield stress term which allows us to describe whether the product behaves like a soft solid at rest before it starts to flow. The key point here is that consumers are making a judgment before any real spreading happens. That judgment can be linked directly to measurable rheology parameters. If we control the yield stress and consistency in a formula, we can design how the product feels the moment the consumer touches it. Once the consumer starts to spread the cream on the skin, the situation changes. The product is no longer at rest. It is now under moderate shear, created by finger movement during application. At this stage, consumers are judging how easy the product spreads, how much resistance or drag they feel, whether it feels thick or fluid while it is moving. This is often the most important part of the application experience because it directly affects the usability and enjoyment. In sensory panels, this is where you hear phrases like easy to spread, draggy, smooth, thick but spreads well. What is important to recognise is that these sensations depend upon motion. They are not properties at rest. From a rheological perspective, this behaviour is dominated by shear-dependent flow. In simple terms, we are asking, does the material thin as it's sheared or does it resist flow? This is captured very well by the power law model through the flow index and the consistency index. Shear-thinning cream where N is less than 1 will feel easy to spread because its apparent viscosity decreases with shear as shear rate increases. This gives the consumers the impression that the product melts or loosens as it's applied. In contrast, a cream with a weaker shear thinning will feel heavier and more resistant to spreading. If the formulation also has a yield stress, then the Herschel-Buckley model becomes useful here as well. Once the yield stress has been exceeded, the power law terms now describe how the product behaves during spreading. The key idea here is spreadability is not a single viscosity value. It's dependent upon the shear rate. By measuring the flow rate behaviour at relevant shear rates, we can link consumer descriptions directly to rheological parameters and describe and design products that spread in a controlled and predictable manner. As the consumer continues rubbing the product into the skin, the shear rate increases further. Finger movement becomes faster, more forceful, and the cream is now experiencing high shear conditions. At this stage, consumers are no longer focused on whether the product spreads easily. Instead, they're judging on the product dynamic, how does it break it down smoothly? Does it glide under the finger? Does it feel sticky, draggy? Does it seem to disappear into the skin quickly? In sensory testing, this is where you hear phrases like it melts into the skin, silky, absorbed quickly, or negatively, tacky, draggy. These perceptions are strongly linked to how apparent viscosity of a product changes at high shear rates. From a rheological point of view, this behaviour is again covered by shear-thinning. Products with a low flow index N show strong reduction in viscosity as shear rate increases. This gives a sensation that the product is becoming lighter, more fluid as rubbing continues. A product that does not shear thin as much will retain a high viscosity at a high shear rate and may feel heavier and more resistant, even late in the application process. This is often associated with more clinical or functional formulas rather than luxurious textures. If we're using the Herschel-Buckley model, the yield stress has already been exceeded at this point, but what matters is how the material flows once it's mobilised. The power law terms describe that behaviour. The key message here is that high shear rheology controls the dynamic feel of a product during rubbing in. By measuring viscosity at relevant high shear rates and fitting appropriate models, we can predict whether a cream will feel silky, fast, absorbing, heavy, and resistant during application. Once the consumer has finished rubbing the product into the skin, the motion stops. At this point, the shear rate drops rapidly, back towards zero. This is what we refer to as cessation of shear. Even though the product is no longer moving, consumers continue to judge how it feels. They notice whether the cream feels substantial or thin, whether it stays where it is or where it was applied, or does it feel like it might run, whether there is a sensation of body or cushioning left on the skin. The sensory panels. In sensory panels, this is where words like cushiony, rich, substantial, lightweight appear. These perceptions are important because they influence comfort, confidence, and whether the consumer feels like the product's doing its job. From a rheological perspective, this behaviour is again dominated by low shear properties, particularly yield stress. A product with sufficient yield stress will resist flow once application stops, giving a stable, non-runny feel. A product with a very low yield stress may continue to flow or spread, which can be perceived as thin or unstable. The Herschel-Buckley model is especially useful here because it captures both the yield stress and the flow behaviour after yielding. Together with the consistency index, it helps describe how much structure remains once shear is removed. The key point is that post-application is not determined during rubbing, but after rubbing has stopped. By controlling low shear rheological properties, formulators can design products that feel reassuring, comfortable, appropriately rich once applied. This slide brings together the key ideas behind everything we've discussed so far, how the mathematical rheology models can be translated directly into what a consumer feels. Let's start with the power law model. This model does not include a yield stress, so it is most useful for describing how the product feels once it's already flowing. The first parameter, the consistency index K, relates to the overall thickness. In simple terms, a higher K means the product feels thicker or richer during use, while a lower K feels lighter. The flow index N tells us how much the product changes as it's rubbed. If N is closer to 1, the product feels similar throughout application. If N is much less than 1, i.e. 0.5, the product shear thins strongly, which consumers describe as melting, loosening, or becoming easier to spread as they rub it in. Viscosity in this context is not a single value. It is the apparent viscosity at the particular shear rate. That is why a cream can feel thick when it's first touched, but light and fluid during rubbing. Now, as we move to the Herschel-Buckley model, this gives us an extra layer of understanding because it includes yield stress. The yield stress, tau0, relates very closely to firmness and stability. A high yield stress gives a cream that holds its shape and feels stable in the jar. It is often perceived as more premium. Once that yield stress has been exceeded, the consistency index K tells us how thick the product feels as it continues to flow. Meanwhile, the flow index N again describes how the product breaks down and spreads as rubbing continues. The key message from this slide is that the parameters are not abstract numbers. Each one maps to a specific part of the consumer experience. By choosing the right model and controlling these parameters, formulators can design products that feel firm, spread easily, break down smoothly, and leave the right after feel, all from measurable rheology data. What we'd like you to do is to please explain rheological terms that are commonly used here in your report. Please, we don't want paragraphs on this. We want very succinct sentences. We want to see diagrams. We want to see equations in your report that explain this. We're very much about the idea. Please don't write long paragraphs that are aimed at just trying to hoover up marks. We're not very keen on that. With AI, that can all be done extremely easily. What we really want is that succinct writing, diagrams, figures correctly labelled and captioned. We want to see equations in there as well. So that I really want to be clear on that. Please make it succinct and short. But that's excellent for your revision. Okay, now for all the creams and ointments that you ran and you produced during your lab, there is a spreadsheet, and the consistency index and the flow behaviour index for each of the formulations can be determined from the graphs that are produced on those spreadsheets. So please download them. I'd say produce a table of those values, and I would start then trying to relate that consistency index and that flow index for all three formulations to some sensory evaluation ideas. Okay, so it's really important to try and move just beyond these are the numbers the test gave. We want that to be related to this is how a consumer would perceive this product when they actually get hold of this. Now please remember, I have attempted to make this a lot easier for you by removing the plastic behaviour, but it's also removed the yield stress, and that's really that sort of how does that product feel when it's first taken out of the jar approach. So that's been removed from you. It does make the graphs much easier to interpret. It makes the process a lot easier. However, the Herschel-Buckley model is not really appropriate to this. However, it's really good that you know about it and have that understanding, and it's a natural follow-on from the power law model. The power law model is the one that you really need to be focused on for this particular assessment. This is a difficult area, rheology. Most people find it very hard to start with. It's not going to be any shame if you struggle with this, if you find it difficult. Please get in touch, but also don't get upset about this, because it is a hard area that is very difficult to come to grips with to start with. We'll attempt to try and do more work on this area during the coming year and a half of the course. It is really valuable. People can get, there are jobs out there really associated with understanding this, and in all honesty, you can put yourself head and shoulders above anybody else at interview if you're able to talk about this with a good degree of confidence. So it is useful. We really are wanting you to understand this for getting jobs. It's not some nice esoteric piece of maths that I'm trying to teach for the sake of teaching maths. It's got very, very real world applications, and the applications run far beyond the cosmetics or the household uses. They can go into incredibly diverse areas such as pouring concrete, tarmacking roads, how thin or thick blood is for prescribing the appropriate medication. It's really it's a very, very interesting and diverse field that has lots and lots of applications. So being able to take this forward into other applications, hopefully you've got a career ahead of you in just this one area. So please enjoy it. Don't get stressed about this. Do talk to us about this. And again, if it does feel as though it's difficult, to be honest, it is difficult. Good luck.